Hello class, welcome to the next section, the last section for chapter 9. This is chapter 9.7, Improper Integrals. So, an improper integral is the integral of a function that either has infinity as its upper or lower bound, or there is a vertical asymptote as one of its bounds, the upper or the lower bound. Okay. So we break these into two types, right? One being that there's an asymptote, the other being that the bound is infinity. So the first type would look like this, okay? The first bound is a, the lower bound is a, its actual value on my function, but it continues on for infinity, okay? So there is no upper bound. We continue with this function for infinity. So now you might say to yourself, well, yeah, the area under a curve that goes to infinity is always going to be infinity, right? Not always. So if we go from a to t, okay, t being a variable for f of x to d of x, exists for every value of t that is beyond a, then this integral from a to infinity of our function is the same as the limit as t goes to infinity of the integral of our function when we plug in t. So it's basically like a change of variable here for the integral function. Okay. B is very similar, except that the lower bound is negative infinity and the upper bound is b. So here we start at a value and we continue to infinity. Here we're moving from infinity to some stopping point b. Okay, so same condition. If my function is from t to b, exists for every value smaller than my endpoint, then the integral from negative infinity to b for f of x with respect to x is the limit as t goes to negative infinity on the bottom to b of my function. Okay, so we would just integrate this, and then we would evaluate from b to t, and then we would take the limit of that as t goes to either infinity or negative infinity, respectively. Right? So that's the first type of improper integral that we have. Okay. These integrals are convergent if the limit exists, right? So if this limit exists and it goes to an actual value, it is a convergent integral. If it does not converge, then it diverges, okay? And the limit does not exist, meaning it just goes on for forever to infinity, most likely, okay? So let's say we have some function, right? We could split this at a, but it starts at negative infinity and it goes on towards infinity, right? So what we would do is we would split this into two parts, from negative infinity to a and from a to infinity, okay? If both of these halves, or pieces I should say, are convergent, then the integral from negative infinity to infinity is us computing both integrals separately and adding them together. So let's do an example. Okay, this is actually a very, very important example. It's very, very generalized, which helps us to understand things that are going to happen whenever we run into improper integrals, but also a lot for what's going to happen later with series and sums in the last section of this course reader. Okay, so note that there's actually three cases when I'm dealing with something like this. So starting from 1 and going to infinity. This is a very actually common thing that we run into. 1 over x over p, there's three things that can happen. P can be less than 1. Okay, so if p is less than 1, that's our first case. When p is equal to 1, that is our second case. And when p is larger than 1, that is our last case. So just think about 1 over x to a power. When p is 1, it's just my function 1 over x, right? So just the reciprocal function. When p is less than 1, we are going to have very small powers here, fractional powers. And in fact, when we get into the negative portion of that, this will actually flip it upside down and make this x to the p power whenever this is negative, okay? When this is positive, large, I'll have very large numbers on the bottom, relatively. And so then this actually should be getting smaller, right? So there's three cases that are happening here. The important kind of pivot point is P at 1. So what happens before 1, at 1, and after 1 changes the shape of what happens here for my function. Okay. Note that my function 1 over x to the p exists everywhere except for when x equals 0 for all three cases. And since my function is from 1 to infinity, I don't even really have to worry about this, okay? Because 0 is not inside of my interval of interest here, right? I'm starting after x equals 0 and moving towards the positive direction. So let's look at this case by case. Again, less than 1, equal to 1, more than 1. So for less than 1, the indefinite integral, right? So without being bounded, of f of x when p is less than 1. First, note that 1 over x to the p is the same thing as x to the negative p. So this will be nice for me to do some calculations. And again, remember here that p is less than 1. Okay, it could be negative. So when p is negative, this is actually a positive value, right? So if I integrate this, okay, the integral of x to the negative p is 1 over negative p plus 1, x to the negative p plus 1. So remember what happens with the power function. You add 1 to it, and the reciprocal of that new power is what's in front. It's the constant in front of your value. Okay. Generally, we would say plus c here, since it's an indefinite integral, right? I'm not evaluating at bounds. I'm just looking at what happens to x to the negative p in general, right? So if I kind of change it around from 1 over x over p to this form, it's a little easier to track what's happening, right? If I start to move stuff around with this, right, I can pull out this negative value so that it's in front, which means this turns positive and this turns negative, right? And the whole thing turns negative. Same thing here, I can pull out a negative from these two and I get p minus 1 in parentheses with this negative that would be distributed. It's just a little bit easier for me to look at, especially since everything has to do with p. I like having something more standardized. If I put this back to how it should be, right, a negative here on the outside means it goes back on the bottom. Okay, it'll be kind of the easiest way for us to start to work with this. And this is defined as long as x is not equal to 0, which we know is not inside of our interval, right? So our integral from 1 to t of 1 over x over p exists for every value of t that's larger than 1, right? The only time this does not exist is when x is 0, and that's not in our interval. So there's a value. So if I'm looking for from 1 and forward, this exists forever, right? So any value of t that's larger than 1, this integral exists. That was my condition, right? If we come here, right? If a to t, if f of x exists for every t larger than my starting value. Okay, so we just kind of verified that this works into my case, since this is only not true, this only does not exist when x is 0, right? So our conditions to evaluate the improper integral are met, so that means that I can do that little fancy smashy thing of looking at the limit when I integrate this. So the integral from 1 to infinity of 1 over x to the p dx is the same as the limit as t goes into infinity for the integral from 1 to t of our function. Okay, so we already found what this looks like when I integrate it. Okay, we already did that work. So I have my negative 1 over p minus 1 times x to the p minus 1 in the denominator. My x value starts at t and it ends at 1 as far as this calculation is met for the fundamental theorem of calculus, right? We do higher bounds first minus the lower bound. And so it's going to look like this. Okay, when I plug in t here, I still have my negative 1 over p minus 1. The bottom is now t p minus 1. Here, when I plug in 1 here, That's 1 to whatever power is just 1, so that's 1 over p minus 1. I'm subtracting a negative, so that's plus. Okay. So if I look at what happens when t goes to infinity, let's look at what's happening here. Okay. T is getting larger. Normally that would mean that this part goes to 0. Okay. So let's just kind of verify what's happening here. I have p minus 1. P is less than 1. So I have a very small value here. Right? So let's say this was like negative 3, for instance, which is less than 1. I would have negative 3. And so whatever value here as it gets large, this would get very large. So p minus 1 is negative, right? Which means that things that look like this goes to infinity, right? A negative value here, it's just like having it on top. So any value with a positive power, right, moving it back up into numerator position, gets very, very large without bounds. And so that's not infinity plus anything is still going to be infinity, right? So this does not converge to a single value, so it's divergent. Okay. So if p is less than 1, this integral, okay, is divergent. Case 2, we're going to do the exact same thing. Okay. But notice that the indefinite integral of f of x when p equals 1 is just natural log of x plus c. So remember, when it, actually I'm sure I wrote this down. Okay, oops. Is 1 is natural log of x plus c, which is defined as long as x is not equal to 0, but anything larger than 0. So open interval at 0, right? Infinitely close to it, but not equal to 0. So our integral 1 to t, 1 over x dx, it exists for every value of t that's larger than 1, because only 1 and above is inside of my interval of existence. I would just have to be careful at 0, which I don't have to worry about. The integral of this is natural log, right? And since we're bounding it, we don't have to use the plus c, right? Just the generalized indefinite integral of 1 over x is natural log. So all of the conditions are met here. I'm not within, I'm outside of this bounds, everything exists. So this integral is the same as the limit as t goes to infinity of this integral. The integral of 1 over x is natural log of x, and I'll evaluate that from t to 1. Okay, and I'll take the limit as t goes to infinity. If you remember, natural log is 0, so I'm really just looking at the natural log of t as t goes to infinity. Okay, and as t goes into infinity, the natural log have really, really large numbers. It continues to climb forever, very, very slowly, but it does climb. Okay, so the limit of natural log as it goes to infinity is also infinity. So when we're looking at p equals 1, this is divergent as well. Okay, so out of our 3 cases, so far 2 are divergent. It's very possible that this last one is divergent as well, right? So let's look at it here. The work is identical to the first part, okay? The only difference is how we're going to calculate our limit. So the limit from 1 to infinity we know exists for all values after 1. The form of my integral is this thing, and remember we're taking the limit as t goes to infinity. It's the exact same work, okay? The only difference here is that p minus 1 is now going to be positive, right? Since p is larger than 1. P minus 1 is still larger than 0 when I zero this out. Okay, so these are positive t to the positive values, which means that the denominator grows very, 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 very large. And if the denominator grows very large, the entire value goes to 0, gets smaller and smaller. So this first part goes to 0, and the limit of this is just a constant, or 1 over p minus 1. So my limit comes to a singular value, which means it is convergent. Okay, so when p is larger than 1, this integral is convergent, and it converges to the value 1 over p minus 1. Okay. If p is equal to 1 or less, this integral is divergent. So let's look at type 2. So that was our exploration of the type 1 integrals. Everything we've done so far was from infinity to a bounds or from a bounds to infinity. Okay, case 3. Oops, sorry, we passed that also. All right, type 2. So here we're using an asymptote happens to be one of our bounds, right? So here, this function has a vertical asymptote at 0. And so I'm looking at the integral from a to 0, that vertical asymptote, right? So if f is continuous from a, but not including b, but infinitely close to b, okay, so discontinuous at that value, then the integral from a to b is the same as the limit as t approaches b from the negative side, right, from the left, right, from the negative direction, of a to t f of x d of x, right? So it's the same sort of thing. We would evaluate this limit, evaluate it from t to a, and then we would approach this finite value, okay, from the left side. B is the same thing. Obviously, it's the opposite side. So if f is continuous on x from a to b, not including b, but discontinuous at a, so I'm sorry, including b but not including a, so discontinuous there, then the integral from a to b, we do the same thing, but we take the limit as we approach from the right side, from the positive side towards a. C is a mixture of both. If f has a discontinuity at c, where c is from a to b, discontinuous at c, right? Then the integral from a to c and c to b are both convergent. Then we can integrate over the entire thing and just add the two integrals that converge from a to c and from c to b. So let's do an example. We want to evaluate from 0 to 5, 1 over the cubed root of 5 minus x. The limit of this as we approach 5 from the negative side, because it's very obvious here that if we plug in 5 in the denominator, we become 0, right? So here, the upper bound is the one that is giving us problems, where we're discontinuous at, and so we have to take the limit as we approach that from inside of our interval, right? So I can rewrite this as 5 minus x to the negative 1/3 power, do a u substitution, so I get du is negative dx. Obviously I'll move this over, so it's negative du is the same as dx, and this turns into a negative u to the negative 1/3 power differential with respect to u. I signify that I'm looking at x's for my variables, right, just to keep me on track and not accidentally plug in the wrong thing. So the integral here is very easy, right? We add 1, so this will become a positive 1/3, and we use the reciprocal of that. Okay, so I'm sorry, a positive 2/3, and so the reciprocal is 3/2. It's still negative here, and then I'm evaluating in x, so I want to replace u with my 5 minus x. Okay, and now I can plug in my t's and my zeros. So I'll have the limit of this for t minus, and then just basically 5 to the 2/3. Okay. So if I look at this, this is still here, this is still here. What happens as I get closer and closer to negative 5? Well, this turns to 0, right? So I'm left with a negative and a negative, which gives me a positive. So now that we have an idea of how to do improper integrals, we can use a helpful tool called the comparison theorem. The comparison theorem really helps us to be able to figure out whether an integral, an improper integral, diverges or converges, especially if that integral is extremely difficult to find, okay? And so the method that we're going to look at here, we are also going to see later on in this course when we talk about series and sums. Okay, so this chapter 9.7 is a very nice look into the future, and in fact we will be coming back and using the methods in this section later on in the chapter, for the last chapter. Okay. Let's say that we have two functions. Okay. They're both continuous, and that f is always larger or equal in value to g. Okay. So whenever we are at a or larger for my x values, right? So if the integral from a to infinity, so from a on, of f is convergent, then g has to converge also, right? Because I'm always larger than this value. And if my larger value converges, then the smaller function has to converge also, right? It squeezes it to convergence. If g, which is smaller, is divergent, then my larger function has to be divergent also. It can't have a non-infinite area under it if it's always larger than a function that has infinite area above it, right? So these are my two comparisons. If my function is larger and convergent, larger everywhere and convergent, the smaller function is convergent. If the smaller function is divergent, then the bigger function has to diverge also, right? So we can use this comparison theorem. And so when we use the comparison theorem, we have to be very tricky, crafty, I should say, right? So the whole time you're using this method, you're thinking in your mind, how can I come up with another function to compare to the function I have that's either larger and convergent, or that is smaller and divergent, right? So those are my two paths to like try to figure out what's going on, okay? So for instance, let's determine if from 0 to pi, sine squared over square root x with respect to x is convergent or divergent. Now, okay, this function is not very easy to integrate. We can use, I guess we could try to use the integration by parts method here, because it is one function times another function, although neither of those tend to go to 0, and we would never actually circle back to our original function because these powers of square root, they'll always kind of change. So this isn't a very easy integral to try to do on our own, right? You can try to do that now if you like on your own and just see how far you get, okay, without trying to do a comparison. Okay, so note here that sine squared is always less than or equal to 1. Okay, for every value of x in R, it'll never be larger than 1. So I can say that sine squared of x over square root of x is always less than or equal to 1 over square root x. I kind of bounded the larger function. Okay. Now this is helpful, but it's not necessarily what I need to solve everything yet, right? The integral from 0 to pi of 1 over square root of x. So remember, this is x to the 1/2 power, okay? Or I guess negative 1/2 power. So I would take the limit as t goes to infinity, right? Because the portion that's giving me problems is a zero on the bottom. So it has an asymptote on one of its bounds. So I would have to approach t from the positive direction as a limit when I do this. So I take my integral, evaluating from pi to t, so I could really just throw pi minus t on the inside there, root pi minus t, to be honest. And this is just a constant, and so I have to look at what kind of value does this approach when it comes, when I approach 0. So as I approach 0, this just goes to 0, right? So then my limit exists and it converges to 2 pi over t. So I took my function and I compared it to a larger function that converges over this interval. So since I have a larger function that converges, this has to converge also. Okay. So this function is convergent by the comparison theorem. This function is also convergent because it is always less than this one or equal to it, and the larger function is the one that converges. Let's do another example. Let's determine whether 1 to infinity of x plus 1 on top, square root x to the fourth minus x dx is convergent or divergent. So we can see that our function has a discontinuity at x equals 1. If I plug in 1, I get 1 minus 1, which is 0. So it has the same kind of discontinuity, so it's a type 2 improper integral, right? One of the bounds is an asymptote. This seems like it's kind of difficult to integrate, right? If I factor here, I get x times x cubed minus 1. That is a difference of cubes, and I can factor that, and then maybe, well, that's really as far as I can get because there's a square root here, right? So nothing would really cancel from that. I really can't do partial fractions from there because it's all under one square root symbol. So I'm sure I could figure something out, but it seems like it'll be a lot, right? So instead, we can try to figure out whether diverges or converges instead of trying to find an exact answer. Maybe that's all the kind of information we need. And so we'll try to find a simpler function that is larger, that converges, or we're going to find a simpler function that's smaller, that diverges. So it really just depends on what's going to happen, on what seems easier, right? So we can find a simpler function smaller than ours on the same interval that's divergent, or a simpler function that's larger that's convergent, right? Either way, let's just start to simplify the function. Let's look for something and compare it to new functions, okay? So we'll probably have to do this more than just one time. Like above, I found a function right away. Okay, maybe I have to do a couple of things and just continue to compare my results as we do. So one thing to note here is I can't find something smaller and then the next time find something bigger and so forth and so forth. If I'm looking for a function that's larger than it, I keep finding larger and larger functions. If I'm looking for something smaller than it, I want to keep finding smaller and smaller and smaller functions. Okay. So again, here we'll write that down. If we simplify our function and the new function that we found to simplify it is smaller, then we would want to continue simplifying towards smaller functions. Okay, and same is true for larger. If I'm trying to find something larger that converges, I keep going larger and larger and larger every time I make a comparison. Okay, so you'll see what I mean as we do this. So to start to simplify the numerator of our integrand in order to make a comparison, that'll be the easiest thing. So if you remember, on top I have x plus 1. So if I wanted to go larger than this, I would find something larger than x plus 1, like something simple, x plus 2, or say x squared. X squared is generally, well, that's not always larger on this interval. Maybe I would just go, I would square this whole term, but that doesn't make it easier. So instead, if I went to just x over x plus 1, right, that would be simpler, but it's always smaller. So that gives me an idea of where I'm going. So if I go from x plus 1 to just x, this is always smaller than this function. So if I'm starting to go smaller, I'm going to do some math here to try to find stuff equal, but if I can't find stuff equal, I'll continue to try to go smaller, right? So that I'm always smaller than this original function. And in that case, I'd be looking for something that diverges because that's what we have for that side of the equality. So since we found a smaller function of simpler form as compared to our function, we should continue to try to find smaller, simpler functions from the one we just simplified. If we're successful, this will lead us in the direction of finding a smaller divergent function, making our original function also divergent. Okay. If our result is not divergent, then we have no result, right? If I keep finding stuff smaller and smaller and smaller and it converges, that doesn't help me because it's smaller than my function. So then I'd have to go the other direction and start to find larger things than my original function that converge. Okay. So going in a simple direction, this is what I start with. I just made one simple thing to make it easier. I just took off the 1, which makes it smaller by 1, at least in the numerator. And then here I simplified some more by just getting rid of this negative x, because that's kind of what threw me off a little bit, right? Factoring that out, and then I'm just kind of stuck. So if I get rid of this negative x here, I'm actually smaller in value because my denominator is now larger, right? If I have something and I subtract something off, I'm smaller in value. So my denominator is now larger, and remember, something's large on bottom is a small number. 1 over 1 versus 1 over 12, right? A large number on bottom means that your number is smaller. So taking something off and making this larger on bottom, the overall effect is that this number here is going to be smaller in value. And again, make sure you know what your bounds are, because if this was negative, let's say negative infinity to 1, then that would be a little bit different, because now everything would be negative. So I'd be like, oh, this is negative and this is negative, and how does that change stuff, right? So simplifying this now, I have x over x squared, which simplifies to 1 over x. Okay. The nice thing is that we saw that 1 over x was divergent from 1 to infinity. Okay. So that means that this function is always larger on the same interval than 1 over x, and this is a divergent function. That means that this has to diverge